Good morning, one and all. Today's academic activity is concerned about the beta-lactamase. The beta-lactamase itself is a very vast chapter, and we should confine, or we are confining this as just a part of it, that is MC beta-lactamases. So before we start about the MC beta-lactamase per se, we are dealing in this discussion that what is the beta-lactam antibiotics, what is the mechanism of action of beta-lactam antibiotics, then comes the beta-lactamase classification, and then we are dealing with the or discussing with the AmpC beta-lactamase overview, what is the resistance mechanism, how can we detect in the laboratory, and what does it mean to a AST report, and how should clinician interpret it. So coming to the beta-lactam antibiotics, this is one of the most widely used antibiotics across the world. It may be the penicillins, the cephalosporins with its generations, monobactam and carbapenems. The mechanism of action of beta-lactams as a whole is the antibacterial activity by binding to specific target protein, that is penicillin binding proteins. These penicillin binding proteins are enzymes which are critically involved in the terminal stage of cell wall synthesis. So basically it disrupts the bacterial cell wall synthesis. Now how it does effect is that it has to bind to the penicillin binding protein or target protein which is there here in the target protein. But for gram negative bacteria, there is one extra step that needs to be done by this beta-lactam antibiotic, is to overcome the outer membrane protein. This has to be done either through porins, then it has to fight with various enzymes like the beta-lactamase, which may be chromosomal or plasmid-mediated, then only it gets access to the protein binding protein. So to get the access of the protein binding protein, it has to pass through the porins. Porins impermeability and how the resistance develops due to porin changes is itself another topic. The protein binding protein penicillin binding protein alteration itself in a is a different chapter, and here we are talking about this beta-lactamase, and that is a small part of beta-lactamase, that is MC beta-lactamases. Now coming to the beta-lactamase, broadly it is the enzyme which hydrolyzes the beta-lactam antibiotics and render them ineffective. It may be chromosomal, it may be plasmid mediated. Now coming to the classification of this beta-lactamase inhibitor, beta-lactamases enzyme, it may be your molecular based, which is Ambler classification, or it is the functional classification which is known as Bush-Jacobi classification. This is the tabular form, that the first column is the Bush-Jacobi classification or the functional classification based on the substrate and action of inhibitor. Here you can see there are four groups: the cephalosporinase, the pelicinellase, which are susceptible to clavulanic acid or beta-lactam inhibitor. Group 3 is metallo-beta-lactamase, and group 4 is which is not classified in the Ambler system of classification. So why the name AmpC? Because it is the C, according to the Ambler classification, it is the C or cephalosporinase. It is usually chromosomal, resistance to all beta-lactam except carbapenems or fourth generation cephalosporin, and these have the peculiarity that it is not inhibited by the beta-lactam inhibitor, that is the clavulanic acid, tazobactam or sulbactam. So what is this AmpC beta-lactamase? In all likelihood, when it is discovered, it was found that it is older than the existence of the antibiotic itself. It dates back to over 2 billion years. So it reflects that the evolution of resistance mechanism to natural beta-lactam produced by this microorganism are actually the biological competition rather than a method for the beta-lactam resistance per se. Now the term, as I have already told you, this term AmpC defines the class of enzyme that belongs to molecular class C of the amylar classification. It has an overall greater hydrolysis of the cephalosporins and resistance to inhibition of beta-lactam based inhibitor as clavulanic, sulbactam or tazobactam. Now, how does it express? Normally, in all the bacteria, this AmpC beta-lactamase is under negative control and thereby inhibiting enzyme production in a susceptible organism. Means, if we are finding it in vitro is susceptible, that means that, or the antibiotic, if it is acting upon a particular organism, that means that AmpC beta-lactamase is under repressor control of a gene known as AmpR. This organism can become induced or de-repressed. That means the repression is inhibited or blocked by mutation, leading to hyperproduction of this beta-lactamase and development of the resistance. Now, before going to the exact resistance mechanism, we can know that what is the regular AmpC regulation, which actually in a susceptible organism occur. Now this is the baseline. This is the cell wall that is constantly recycled, forming the oligopeptide. This is the outer membrane of the gram-negative bacteria, and here in a normal circumstances these neuropeptides are transported through the AmpG gene and it is processed by another gene known as AmpD gene. So by processing of this AmpD gene, it is inhibiting the competition with this UDP and acetylmuramic acid, which is the substrate for AmpR, and this AmpR will directly lodges with this AmpR and it will effectively repress the AmpC gene. Now what happens when a inducer comes into play? This recycling will be more neuropeptides will be generated. This more neuropeptide will not be able to handled by this AmpD gene. It opens a gate for these neuropeptides to compete with these UDP and acetylmuramic oligopeptides, and it may happen that it attaches with the AmpR in the binding site. That leads to a conformational change, and that is the induction of the AmpC gene. Here it is to be noted that if in a timely manner, if we remove this inducer, this may get back to the original position. But what happens that when a constant exposure of this inducer occur, it may happen so that this AmpD gene get mutated. Once it is mutated, there is always a possibility of chance that this neuropeptide will only bind with the AmpR binding site, leading to constant redepression or derepression. It is derepression. So that derepression will be there in the organism, which will constantly inhibit or constantly increase the AmpC beta-lactamase production. That will lead to the resistance mechanism for beta-lactam antibiotics. Now coming to the mechanism by which these beta-lactamases increase or act upon the beta-lactam antibiotic, it may be by a inducible resistance by chromosomally mediated AmpC gene. Example are there: Enterobacter cloaci, Serratia marcescens, Citrobacter frondae or Pseudomonas aeruginosa. there may be another type of AmpC gene which is non-inducible but it is chromosomally mediated. Example, Escherichia coli, Shigella, and then comes the transferable, the plasmid-mediated resistance. It is mostly seen in Klebsiella, E. coli, Salmonella, or rather nowadays it has become a norm that plasmid-mediated AmpC are there in most of the clinically isolated bacteria in a clinical microbiology laboratory. By definition, this inducible expression is reversible, as I have already told, but strains that producing inducible AmpCs can easily segregate mutant and they become the major population by selection, and that resulting in constitutive expression. The usual AmpC inducing organism harboring this inducible AmpC are all Enterobacter species, all Sericea species, Pseudomonas aeruginosa, Providencia, Morganella, and there are many other non-fermenting gram-negative bacilli also that harbor this inducible AmpC gene. So, based on the propensity what triggers this induction, we can divide or rather vaguely classify what is a potent inducer or what is a weak inducer. So it may be classified as 4 types. One is potent inducer but labile beta-lactam compounds. Those are the first generation cephalosporins like the cefazolin, the cefamycin like the cefoxetine, and clavulanate. They are potent inducer as well as they are get inactivated by presence of AmpC. Second is your potent inducer but stable beta-lactamase. Carbapenems comes into this group, particularly imipenem. Imipenem is a strong inducer, but it renders, it is stable against the AmpC and it may act if in a AmpC producer. Second is weak inducer and labile beta-lactam compounds. This is the main point of contention, and these are mostly the uridopenicillin like the piperacillin and the third generation cephalosporin like your ceftriaxone, cefotaxime, and ceftazidime, because these are weak inducer, but in presence of clavulanate it may express or it may induce more AmpC, and because these are labile beta-lactam compounds, it will be inhibited or their action will be inhibited by AmpC beta-lactamases. Next comes the weak inducer and stable beta-lactam compounds. These are mostly the fourth generation cephalosporin, particularly the cefepime. Coming to the non-inducible chromosomal resistance, mostly the E. coli, because it expressed at negligible level, clinically not relevant, but occasionally it may so happen that there are duplication and mutation in the promoter genome NC and they may hyperproduce, but this is negligible. Now the most common AmpC production in E. coli is also due to plasmid-mediated AmpCs. Coming to the plasmid-mediated resistance, there are almost more than 20 different AmpCs that has been till now found, and this list is growing. Now, how does there are around 5 phylogenetic groups. One is Enterobacter group. These are their genes that they have these plasmids that occur during the originating from their respective chromosomal organism. So it may be Enterobacter group, Citrobacter frondi group, Morganella morgani group, Hafnia albae group, and the Aeromonas group. Among these all plasmid-mediated AmpC, the most common is the CMY2, which is present worldwide. Now, This plasmid MC usually constitutively expressed and conferring resistance pattern similar to that of de-repressed chromosomal MCs. However, these genes, if you can see that there are various kind of genes. So here, if you see ACT1 or ACT1, DHA1 and 2 and CMY13 are linked to AmpR genes and are inducible. So if we are experiencing any inducible MC gene or MC phenotype in a clinical microbiology laboratory, we may assume that these may be the genes and we need to confirm it by the molecular methods. Suppose in E. coli or Klebsiella, if we are experiencing a inducible resistance mechanism, we need to confirm that whether these are present, these plasmids are present in that particular isolate or not. Now, how we can get a clue for MC presence in our routine AST practice? First is your combination of resistance to oxyimmunocephalosporin like cefotaxime or ceftazidime. It will be resistant. Cefamycin like cefoxitin is resistant and susceptible to cefepime. It will give a clue that this particular isolate may be a producer of MC. This strategy, however, will not detect ACC1 gene where the cefoxitin is not inhibited, and it will give a susceptible phenotype. Then the flattening of third generation cephalosporin across a or beside a strong inducer like imipenem or clavulanic acid. Imipenem kept in center, which we are practicing in our laboratory, will give a clue if we put around the third generation cephalosporin, keeping the imipenem disc at the center. Now, the other likelihood is resistance to cefamycin and beta-lactam inhibitor combination and susceptible or intermediate to third generation cephalosporin. This may also give a clue to the MC production, but all this said, it is not said that simple. There are various of resistance mechanism. There is ESBL. There is ESBL which is not inhibited by the beta-lactamase inhibitor, and there is also presence of carbapenems. So in absence of pure susceptible carbapenems and absence of ESBL, this methodology can hold true, but to get an exact figure or exact mechanism of MC, it is not at present possible. Coming to different tests, presently CLSI doesn't have any recommended method for detection of MC genes. However, most probably they are working on it, and we may have a recommended method by next CLSI M100 revision. Other tests that can be done and published in literature are Dick's potential test with cefamycin or third generation cephalosporin alone and with cloxacillin or boronic acid. Cloxacillin and boronic acid, these are not inhibited by MC beta-lactamases. So if we put cefamycin like cefoxitin, and beside that if we put cefoxitin with cloxacillin or boronic acid and we get an elevated zone at least more than 5 mm, then the cefoxitin disc alone, we may think that this might be an MC producer. Second is the double disc synergy test, again with cefamycin or third generation cephalosporin alone and with cloxacillin or boronic acid. Here what happens that with the cefoxitin disc or third generation cephalosporin disc, we just place another disc, blank disc, and we charge with your either cloxacillin or boronic acid. So if there is a zone which is or where there is an increased zone, then we can tell that this is a double disc synergy test. Now, E tests are also available with at one end cefoxitin alone, and on the other end cefoxitin with cloxacillin or boronic acid. A 3 dilution decrease in MIC will suggest that this is an AmpC producer. Coming to the 3-dimensional test, the various modification with 3-dimensional tests are there. The organism, or here the basic methodology is we take a susceptible organism for 3GC or cefamycin. Most commonly taken is E. coli 80cc25922, and to that we just charge after we just long culture on a molar Hinton agar plate, and we just bore a slit or a radial punch is done, and there either directly the test organism or the extraction of the test organism is made. So if there is AmpC production, there will be a denting of zone around the E. coli susceptibility. But having all said and done, this phenotypic test cannot reliably detect whether it is chromosomal or plasmid mediated. You need to do molecular test. There are various literature depicting multiplexing. Also, there are various literature tried to standardize this method in real-time PCR also. Now, what should be in the AST report? Once we get such type of phenotype, what can be done? That depends on the local hospital practice and the AMSP team of that hospital, how they want to go about it. If whether they want to just report it as it is with a comment that possible AmpC producer. It may also occur that if the isolates are higher and the organism isolated from critical sample like blood or body fluids, then the laboratory may report it as third generation cephalosporin and piperacillin tazobactam as resistant, or fearing that it may be used, we may totally omit the total reporting of third generation cephalosporin or piperacillin tazobactam. So 3 possibilities are there. That depends on the capacity of the AMSP of that particular hospital, the ID specialist, and the teamwork between the internist, the general medicine, and the microbiology laboratory, that this can be sorted out. Now, what is the clinical impact? The bacteria producing inducible AmpC may turn out to be resistant with even 1 day of giving a strong inducer with the treatment. Like the most common what is being prescribed is amoxicillin clavulanic acid. By knowing clavulanic acid is a strong inducer, that particular bacteria may turn resistance even after 1 day of treatment also. Now, these weak inducer, strong inducer, that are the in vitro terminologies. We cannot predict the how the bacteria will behave in vivo. If suppose we are by convention we are giving a weak inducer, but if there is ample number of production of that bacteria or ample number of AmpC gene are there, it may turn out to be resistant. Now, in such cases, we may give a clinical note that AmpC producing isolate has been isolated. Kindly repeat within 2-3 days to know that whether still that organism is susceptible to that organism or that antimicrobial or not. And all after doing so, because these are not in vivo, that may lead to failure of treatment also. Now, what is the treatment recommendation? This treatment recommendation is mostly came out in 2021 by the IDSA, that in case of moderate to high risk organism like Klebsiella aerogenes, Enterobacter cloacae, or Citrobacter friendly third generation cephalosporin and Piperacillin tazobactam are not recommended, and in this case carbapenem should be used, more so meropenem or ceftazidime avibactam, because avibactam is non-inhibited by the AmpC beta-lactamases. In case of low risk organism like Salacia, Provincia, or Morganella, we can treat according to the AST report. If in the AST report it is coming susceptible, we can go with third generation cephalosporin or Piperacillin tazobactam, and if it is coming resistance, alternative method can be seen. Other studies are there where they have advocated with the combination therapy, and that combination therapy, they have found that with a carbapenem, if fluoroquinolone is added, the response is more than when carbapenem is combined with aminoglycosides. The treatment response is more in case of fluoroquinolone. So to conclude this, we can say that we have to be in this age of when everyone is now more or less are aware with the ESBL production and the treatment methods or treatment modalities for a ESBL producing isolate. We need to be vigilant for AmpC beta-lactamase also, and we need to have this testing procedure in to develop a at least screening procedure to detect AmpC, and we can directly convey to the clinician about the treatment option. Thank you.